Hello there. Today I'll be talking about this Hack CPU HDL implementation. So right away looking at the CPU inputs and outputs here, it's receiving one input from the M register, as you can see coming around here, one instruction input, which is coming from the ROM, one reset bit as well, which if hit restarts the program. It's also outputting one 16-bit value to the M register, which is in memory, 1 bit, which will determine whether that M register is writing, storing that value, or if it's being read, and one 15-bit address value, which determines which registers are accessed inside that memory, and then some program counter bits, which determine what instruction is going to be read from the ROM next. So breaking this down into parts of what happens inside the CPU, we can see that first we do some instruction checks. This is basically just creating 2 bits, A ints and C ints, to determine whether the instruction is an A instruction or a C instruction. It does this because an A instruction always starts with a 0 bit, and by not selecting that bit, that becomes a 1 bit. Therefore, A ints is 1, and then flipping that again, C ints becomes a 1 if it's a C instruction. Then we move over to this A register. We can see a multiplexer just before it. What these next parts do is essentially select between the ROM instruction or the ALU output to determine what enters that A register. And so this AND gate here beforehand is basically saying if the instruction is a C instruction, and if the D1 bit is set, which I can show you here, remembering that D1 determines if the destination of the C instruction goes to the A register. As we can see, every time a 1 is in D1, A is there as a destination. And that's just checking if those 2 conditions are met, and if so, then the ALU output is routed into the A register. And this multiplexer right here checks if those conditions are met. If not, then it forwards on this instruction from the ROM straight into the A register. Moving on, we can see an OR gate here. If it's an A instruction, and if the ALU output is being routed into the A register, then set this A register's load bit right here to 1, which basically means it's going to store whatever value it's getting to it, which is that ALU output right there. Our next part here is a multiplexer again, and this is this one right here, which is basically checking the A out bit and the in-M bit, and it's basically just checking if this bit is set, if it's a C instruction. And that bit right there in our C instruction is determining whether, as we look here, if we compare these two, we got A equals 0 and A equals 1. If A is 0, then the A register gets passed on. If A equals 1, then the M register gets passed on. And we can look at all these conditions, it's the same thing. Not A, not M, negative A, negative M, and so forth, even when we have the D register involved, D and A or D and M. And it's all determined by this A bit here, whether that A bit is set to 0 or 1. And that is what this multiplexer is checking here with that instruction bit right there. And if it's set, then the M register is routed to the ALU, straight through here. Otherwise, it is the A register. Moving on, we've got another AND gate here. And this is just checking, again, the destination bits of that instruction. So if it's a C instruction, and that D2 bit is set in that instruction, this bit right here, and we just look at that, that means that the D register is a destination. So that will then set the D register to write whatever value it receives. And as we can see here, that will be that bit right there. Moving on, we've got the ALU. This receives, determined by this multiplexer just here, whether we get the M instruction or the M register or the A register value, and the D register value. It also receives, obviously, these comp bits here, as they determine what function is done between those two inputs. And then outputs the ZR and NG bits to the program counter. And these just basically tell the program counter whether the output value is equal to 0 or if it's negative. And that will determine whether it's jumping to the instruction it's given or whether it's just going to default increment. And now this ALU output is sent out of the ALU, but these next couple of parts determine where that output is sent. So first we've got this OR gate here, and this is basically just sending the A registers, it'd be right here, this A registers value straight out to the address, the M register address. So that would be determining what registers within the memory module are being read or writing to. And then we've got another OR gate down here. This would be this one right here, and this is determining whether this sends the ALU output to the registers that were just selected by this OR gate here. And finally, we've got an AND gate, which is just checking if it's a C instruction, and if that D3 bit is set. Remembering back here, D3 bit is determining whether the M register is one of our destinations. So of course, that is then going to forward on a write bit to the M register in memory, which is going to write whatever output it is receiving. Moving on, most of this stuff is now determining what the program counter does by doing a bit of math on some jump conditions. So first off, we've got an AND gate here, which is checking if that ALU output was equal to 0, and if the J2 bit is set. Right here, J2 is the jump if equal to 0. And of course, we can see jump if greater or equal to. There we go, and that will then set JEQ to 1. We've got another AND gate here, which checks if the J3 bit is set and if the ALU output is negative. Bring the J3 bit. That is checking if the J1 bit is set and if the ALU output was negative. If so, the JLT, jump if less than bit, will now be set. Now I've got an OR gate here, which checks if the ALU output is 0 or if it's negative, and then sets this variable here 0 or negative to 1. If that bit is not set, this flips it to create a positive bit, which will be 1 if the value is positive. Otherwise, it's going to be 1 if it is 0 or negative. Now I've got an AND gate here, which is just checking if our positive bit is set, so our ALU output is positive, and if our J3 bit is set, which was our jump if greater than bit. So that will then set JGT as variable to 1, because it will jump as the ALU output is positive and the JGT bit is set. So we've got another OR gate here, which is basically just checking if our jump if equal to bit is set, or if our jump is jump. If less than 0 is set, then obviously we can jump as it's less than or equal to 0, which sets us up for this OR gate here, which is basically just checking, if we're jumping due to the result being less than or equal to 0, or if we're jumping to the result of the ALU being greater than 0 and that being selected in the instruction, then we set this jump to a variable to 1. And that is just checking, again, down here in this AND, a final check, essentially, that that is the C instruction. And our jump to A bit is set after all of that. We then set this PC load bit to 1, which is basically saying, if all of these conditions are met, we can now get ready to load a new address into the program counter. That's what all this is about, basically. And then moving on, we've got if those conditions are not met and we are not jumping, then the program counter will default to increment. So that's just saying that one of these will be 1, well, the other will be 0. We're either incrementing the program counter to the next instruction in the ROM, or we are loading a new address ready for a jump. And that is what this program counter chip does. It will receive those inputs, the A out, which is coming from the A register, the increment bit, the load bit, one of these will be 1, one will be 0, the reset bit, that will set the program counter back to 0, that comes externally as well, and then the out bit, which goes to the program counter and grabs our next instruction from the ROM. And that is essentially all this HDL implementation of a Hack CPU involves. So thank you for watching. Enjoy the rest of your day.